Welcome to another unit in the ISM Statistics 1 exercise set. This time with an exercise on measures of contingency. Let's take a look at the exercise. To quantify if there is a relation between gender and the evaluation of YouTube videos, a survey has been conducted and the results are summarized in the table below. Calculate a suitable measure of association to quantify the relation between the two variables. Let's think which measure of association we can actually calculate here. Well, overly good, overly bad. This could be a variable where we can say, well, this might be ordinal because we can rank them. However, if we take a look at male and female, here with gender we clearly cannot insert any kind of ranking. Therefore, at least one of the two variables is clearly nominal in nature. And therefore, we need the chi-squared statistic or something building on the chi-squared statistic or something like the Yule coefficient. However, here we stick with the chi-squared statistic. How to get it? First off, we need the marginal frequencies. And for the marginal frequencies, we copy the table from the exercise and extend it by one additional column and one additional row. In those rows, we calculate the sum over all the columns, or the corresponding column, and the corresponding row. So if we start, for example, with males, we add 13 plus 28, we get 41. Same for females, we get 52. And for overall good, we get 44, overall bad, 49. Then finally we need to add at least one of the sums, so we get an overall amount of participants, overall number of observations of 93. This then is the first step. We're going to use those marginal frequencies in calculating our expected frequencies. We can do this with the following formula, whereas the Ni star or N star y, they are the marginal frequencies we just calculated on the slide before. So we copy again the table here only with the marginal frequencies. We leave blank the cells in the middle because here we will enter our expected frequencies. How do we get them? Well, for each cell we select the corresponding marginal frequency according to the column and according to the row, multiply those two and divide it durch the overall number of observations. So for example, overall good, male, we have 41 times 44 divided by 93, giving us as a result 19.4. Then for the next one, we get female overall good. This would be 44 times 52 divided by 93, leading to the 24.6 we have here. Then the same for overall bad. Here for males we have 41 times 49 by 93, giving us this, and females the same, 42 times 49 by 93, giving us 27.4. By using those expected frequencies and the original frequencies, which we can summarize in this table, we can then calculate the chi-squared statistic. For the chi-squared statistic we have this formula, which in the end means nothing else than take the expected value, here the values after the slash, subtract the original values, the values before the slash, and square the result divided by the expected value. So for example, for the first one, overall good, male, we have 19.4 minus 13 in parentheses to the power of 2 divided by 19.4. We do the same thing. Will look like this. So for female and overall good, we have 24.6 minus 31 to the power of 2 divided by 24.6. We can see here we have 4 cells. We calculated 4 expected values for expected frequencies, and we get 4 terms for the chi-squared statistic. And this is always the case. So we directly see whether we missed something or we got everything we need for the chi-squared. Well, if we calculate what's given here, we get a value of 7.1675. We could finish at this point because the task just said calculate an appropriate measure of association, or we could carry on and calculate a measure of association which also takes care about some biases inherent in the table. Those would be, as seen here, the contingency coefficient and the corrected contingency coefficient. The contingency coefficient will take care of the number of observations, and the corrected contingency coefficient of the size of the contingency table. Why are those two parts important? Well, if we have more observations, our chi-squared might get bigger. Might get bigger because more observations mean more potential for deviations. We can have larger deviations between actual and expected values. So the overall trend points into the direction more observations, larger chi-squared. Then something similar could be said about the size of the table, of the contingency table. We have a larger contingency table, meaning we have more possible cells we need to consider, meaning if we calculate the chi-squared statistic, we will add up more terms. We directly see there's a potential, if we have more terms, to also get a larger chi-squared statistic. So we need to control or correct for both of those two parts, and we do this in the following way. First off, if we take our chi-squared and for the contingency coefficient transform it in this way, so we take the chi-squared, divide it by itself plus the number of observations, and then take the square root, as done here in this example, where we get a result of 0.2675. We've taken care of the first problem, the number of observations. If we then skip over to the corrected contingency coefficient, we take a look which is the smallest one, the number of columns or the number of rows. Here we have 2 times 2, so they're both the same size. So the answer here is that this parameter m will just become 2. We need this parameter m to get this correction factor, which is just m divided by m minus 1, and then taking the square root of it. So here we have 2 by 1, so we have the square root of 2 as a correction factor. So we multiply the square root of 2 to the contingency coefficient, yielding here as a result a contingency coefficient, corrected contingency coefficient of 0.3783. This then concludes this exercise. I hope you enjoyed listening to it and learned at least something from it. So until next time, see you and goodbye.